Driving forces for the reactions? Well, it depends on what type of reaction. Tell me what type of reaction and then do it.
There could be gas evolutions, precipitations, and single replacements or double replacements, I think.
Okay, but if it's a single replacement or double replacement, it's not necessarily a driving force. You could have a single replacement pattern, double replacement pattern that doesn't have a driving force. And so the first two were fine, gas formation, precipitation, for what type of reaction? Metathesis. And
Metathesis.
Also strong acid to weak acid.
yeah, it doesn't have to be strong, it just has to be stronger to weaker. And so it could be like a weak acid going to an even weaker acid, which is fine. Okay, what else do we have?
More active to less active.
More active to less active for single replacement, okay. And what else?
Strong.
Did I talk about this yesterday? Driving force? A little bit. So for example, will gas formation work in redox reactions? Will gas formation work in single replacement reactions? No. Yeah, that's good. Okay. So for redox, we go from more active to less active, oxidizers, reducers, acid-base reactions, stronger. But Lewis is a bit more tricky. I talked about the hard, soft, acid-base stuff, but you don't have to worry about that. For Lewis, what we do is we have to do a mechanism. You know what a mechanism involves? A mechanism involves following the electrons. What do we follow in Lewis acid-base reactions? Let's see, hopefully this pen is going to be okay. For Lewis acid base, you have to show me the arrows, and the arrows show me what?
You need the lone pairs?
Yeah, how the lone pair, because Lewis base is lone pair or electron pair donor, and Lewis acid is electron pair acceptor. So you have to show me what's called the mechanism for the reaction. And so if I asked you to show, what I meant by showing is you got to show me how they react in a Lewis acid base reaction. So we could treat water as a base and CO2 as acid, or vice versa. It would lead to different products. In this case, this is the preferred. So water is the base, CO2 is the acid. And so if this lone pair goes in here, what's got to happen? One lone pair gets booted out because carbon can't have more than an octet. And then we show this in steps, what happens here. And so what happens here is that we're going to form this. How I have this oriented, this depends on how you want to orient it. Whenever there's a non-zero formal charge, you have to show it. So we show the non-zero formal charges like this. And then what can happen is vibration here, like that. Leave this there. So we show it step by step, mechanistically. Lewis structures, we don't really care about the three-dimensional aspect of it. But, is there driving force? It turns out that this is less stable. Even though it's less stable, a little bit can form. In terms of energy, it's better to have CO2 and water. Here, so most of the population will be CO2 and water, but some might be able to react up here to form carbonic acid. And what we end up with is, we end up with something called dynamic equilibrium. When we look at the Maxwell-Boltzmann distribution, you know, there's gonna be a certain population that can always make it up the hill. Even though carbonic acid will decompose spontaneously, some more of these will collide and undergo this mechanism to reform carbonic acid. So there's gonna be a small quantity of carbonic acid. The bulk of it will be CO2 and water. Now, this is what I mean by showing. You gotta show it mechanistically, how it reacts to form carbonic acid. And this is what makes Lewis acid-base reactions more complicated than Bronsted. Bronsted is just proton transfer, and it's not difficult. Not as difficult, I should say, as Lewis. All right, to stay on schedule here, I want to get into chapter 6, which deals with gases. So we have gas pressure, the simple gas law, the combined gas law, also called the general gas equation, and the ideal gas law. Applications of the ideal gas law. Gases in chemical reactions, mixtures of gases, kinetic molecular theory of gases, gas properties related to kinetic molecular theory, non-ideal. So a lot of this is just kind of repeat of intro, but some of it, yeah. So gas pressure, let's take a look at that. And what we'll do is we'll also throw in some kinetic molecular theory, you know, in this. Kinetic means what? Yeah, and so this is in molecular motion, 6-7. It's not all molecules. It could be atoms, like helium gas doesn't form molecules. But if we have a gas like this in a container, there's going to be collisions with the walls of the container. In fact, there's going to be collisions with all the walls of the container. And so what we find for a gas is that the pressure on all the walls is the same. And the pressure is equal to the force of these collisions per unit area. Force could be measured in like physics, units in physics. Do you know what the unit of force is in physics? Newtons, yeah. And so typically this is in newtons per meter squared. Yeah. Newtons per meter squared. But we have other units for pressure, so let's probably just take a look at all the pressure units that we have. I'm going to deal with. A Newton per meter squared, do you know what that's called? I'll give it a name.
Pascal.
Pascal, yeah. Newton per meter squared is also called a Pascal, which is defined, this is defined as a Pascal. PA. After,
Do you know why they call it Pascal?
because Pascal was a famous scientist studying gases.
I figured it was either named after something.
Yeah, it's named after somebody.
Like,
Here, it is. Pascal honors Blaise Pascal, 1623 to 1662, who studied, I'm sure I'm mispronouncing that.
I thought it was
Pressure.
I
I thought it was
you're not, that's a cool name.
Yeah, it's pretty good. So what are the units that we use for this? Pascals is one of them.
Yes.
Yeah, millimeters of mercury.
Our
Right.
atmosphere.
Atmospheres, yeah.
Yeah.
I thought there was one other though. Isn't
So we have one atmosphere. One atmosphere is, looks like it's defined as 760 torr, which is,
Exactly equal to 101,365
yeah,
Pascal.
right. So one atmosphere, this is normal pressure. Atmospheric pressure. Normal atmospheric pressure is at sea level. You know, if you go up in elevation, then you don't have this thick of an atmosphere blanketing you. And normal atmospheric pressure is equal to 101,325 pascals. Exactly. Or they say, what do they say, approximately?
No, they say exactly, with, approximately equal to 101.
Yeah.
760 torr is exactly equal to Pascal.
Well, let's look up here. One standard atmosphere is defined to be exactly equal to 101,325 pascals. That's a huge number. So oftentimes it's abbreviated 101.325 kilopascals. So I bought a bike tire the other day. The bike tire had the pressures in kilopascals. You know, it's like fill it to 200 kilopascals. I forgot the exact number, 107 kilopascals. But, you know, this is not that common. I guess in Europe it's quite common, pascals and kilopascals. Probably what's more common is the bar. Do you know what the bar is?
1 atmosphere is equal to 1 bar.
Close.
It's 1.013.
1.01325 bar. So they're about 1% difference here. That's good. And so a bar is equal to 10 to the 5th pascals, is a bar, 10 to the 5th pascals. But usually people just remember this. 1 atmosphere is 1.01325 bar, which is equal to 1.01325 times 10 to the 5th pascals. And so kilobar is kind of, kilopascals is fine. A kilopascal is like, what kind of unit would that be like?
A kilogram.
A millibar.
Yeah, a millibar. What is a millibar? A millibar is is equivalent to 1,013.25 millibar. And so the relationship is like this. 1 atmosphere is just roughly 1 bar. And 1 millimeter of mercury, which is equal to 1 torr, which is about equal to 1 millibar. And so people talk, and rather than talking in terms of millimeters of mercury, they'll talk in terms of millibar. And rather than talking in terms of atmospheres, they'll talk about bar. But the problem that, and this is why I'd like to use atmospheres. I like to use atmospheres because it's an easy number to remember. What is the normal pressure? Normal pressure is 1 atmosphere. And so the pressure here is very close to 1 atmosphere. Versus what is the normal pressure? Oh, the normal pressure is 1.01325 bar. But people are switching here. So what they're saying is, because they can define torr as anything, 760 torr is exactly equal to 101,325 pascals, and so this is exactly equal to 760 torr. So this is what we're going to do. We'll just reuse this by definition here. And then 760 millimeters is close to this in Pascal, so it's not exactly, but you know what? People don't really worry about it at all. And so they'll just use this as 760 millimeters of mercury. And they'll say a torr is equivalent to a millimeter of mercury, you know. So people don't worry about the difference so much. So thus, in this text, we will use pressure units of torr and millimeters of mercury interchangeably, meaning that we're not going to worry about it. Slightly different. All right, now, this is kind of a weird unit, millimeter of mercury. This, a Pascal, I can visualize. A Pascal is you're going to have certain newtons of force, so the collisions against a meter squared of wall. But, you know, how is a millimeter of mercury related to pressure? Because a millimeter of mercury, this is length. This is a unit of length. Actually, it's a unit of height. But, you know, millimeters is length. And so how is that related to this? The way it's related is we look at liquid pressures. And so when we look at liquid pressure, it's like this. Let's say I have a square centimeter here, and I'm going to fill this up with air, the atmosphere. How high does it extend? How high does the atmosphere go up?
As far as an atmosphere.
I don't know, miles?
We don't know.
Yeah. And so it goes up, it's like miles. So what we can say, I don't know the number, but let me just take a look at this, or somebody can search it.
For what?
What is the height of the atmosphere?
What's the height of the atmosphere?
A couple thousand kilometers.
What did you say, 100?
What?
No. From
6,214 miles. Okay.
That's what I said.
So we could represent the pressure of the atmosphere. What is the normal pressure of the atmosphere at sea level?
What atmosphere?
1 atmosphere. And so 1 atmosphere is equivalent to 6,214 miles of air. And so this is a different way of expressing the pressure, you know. You're going to have that many miles of air, and that's going to weigh on you. If you have fewer miles, then it's going to weigh less, right? And so if you're at high elevation, you're going to have less air. The problem with air is its density is not linear. That is, you know, down here near sea level, it's quite dense. But as you go up, it becomes less and less dense, right? It's less and less dense. So this is kind of non-linear. This is non-linear.
Thank you.
And so let me put this in like kind of quotation marks here. Okay, now we're going to construct a balance here. Do you know how much this 6,214 miles of air weighs? You know, if I put a scale down here, do you know how much it weighs?
1 atmosphere.
Yeah.
how many-
No, I mean how much it weighs?
In grams?
No, I mean grams would be
Such a big number.
yeah, it would be pretty big. Pretty big.
So how do we know how much it weighs?
Some people have it memorized. Do you have it memorized?
No.
I do,
Currently.
but let's see where it is in the book.
I haven't seen that number before.
How much does an atmosphere weigh?
The weight of
600.
The weight of the atmosphere, you don't know how much it weighs?
760 millimeters mercury.
I'll tell you how much it weighs. Why can't I find that? That's weird. It tells you in the book how much it weighs.
A couple of tons.
Oh, here we go. Oh, wow, it's not here. It's not here. 6.1. We're missing something. You know what we're missing? It would be on the inside cover of the book. But I have it memorized. You know how much this much air weighs?
How much does it weigh?
This much air weighs 14.70 pounds. And then what I'm going to do is I'm going to make this 1 square inch rather than 1 square centimeter. So if I have a square inch like this, it's going to be 14.7 pounds per square inch. And do you know what we call it?
PSI.
Yeah, PSI. So this is going to be 14.70 PSI, pounds per square inch. So we're going to have that many pounds. 14.7 pounds, I mean, that's 6,240. It doesn't weigh that much, really, does it?
No.
And 14.7. Actually, you don't notice it because we live under an atmosphere of air. But, you know, sometimes you can feel it, like if you're riding a bicycle or something, you'll feel it, right? Or if you stick your hand out the car window, you'll feel it. You know, you're swimming through this atmosphere of air. 14.7 pounds of it. Let's do some equivalent things here. I'm going to do this. I'm going to take an inch squared. Now I'm going to fill this up with water. If I fill this up with water, water is a lot more dense, right? This is like 1,000 times more dense than air. This is nonlinear here. And so if it's 1,000 times less dense, then you'd think you'd use 1,000 times less. 1,000 times less would be 6 miles. So 6 miles of water, but that's not the case. It's not the case because, you know, air gets really thin the higher you go. Water really isn't gonna, you know, there's gonna be a difference in pressure and density. So for example, at the bottom. But if we filled this with water, do you know how high I have to build this? If this were liquid water, H2O liquid. H2O liquid is a lot more dense, and then the density doesn't change much as we go up. So it doesn't get thinner and thinner, you know. It does, but it's so negligible. So if we wanted this to be 14.70 pounds of water, how tall would this be? How tall this would be about
14 feet or inches.
not 14 inches. It's actually a bit taller. 14 feet is too small. You know what it is? It's about 30 feet. So this would be about 30 feet of water, liquid water. So we can use the length. The length is the height, you know, and so this would be 6,214 miles of air or 30 feet of liquid water. 30 feet of liquid water would weigh 14.7 pounds of 1 square inch. Does that make sense?
Yeah.
Yeah. What's the most dense liquid you can think of?
Mercury.
Mercury. And so if we use mercury instead, how you know, if I want 14.7 pounds of mercury on a square inch, how much mercury do I need?
760.
760 millimeters. So here I just need to fill this by 760 millimeters. Because mercury is so dense and weighs a lot. And so this is 760 millimeters of mercury. And that would be equivalent to 1 atmosphere, which is equivalent to 14.7 pounds per square inch. So what we can do is we can do some more quantitative calculations in here. And so the density of a liquid is given oftentimes a different symbol. Sometimes it's given the same symbol, D. But let's see what our book used for the density of a liquid. D. Our book is just going to use D. Density of liquid. A height is not really a pressure. You know, this would be 760. Actually, this is equal to 760. 760 millimeters of mercury. Here. But pressure, pressure is going to be in units of Pascal. And so how can we get that? And so the pressure of a liquid is equal to, this is the equation, it's equal to the force over the area. The force is the weight, and so it's equal to the weight over the area. The weight is equal to G, which is the gravitational constant times the mass. You don't need to know this, etc. And so when we're looking at the pressure of a liquid, the pressure of the liquid is going to equal G, which is the gravitational constant, times the height, H, times the density, D. This is where G is equal to 9.8. I don't know how many sig figs they want us to do this to.
4.
3? Usually people memorize 3, 9.88. Let's see what they do. No, actually they haven't. Look how many sig figs they're using.
Oh, yeah, 5.
Wow, okay, we're going to use that many sig figs then.
9.80665.
Okay, 9.80655 meters per second square. And these are the units for gravitational constant, G.
Professor, it's 9.80665.
Okay, thanks. 9.80665.
It says both.
Oh, where am I looking? I was looking at this one.
I was looking at the one in the actual
Yeah, you're
equation.
looking, so this is a typo that they have in the book.
Oh.
And so let's look at G and confirm which one's correct.
Which one is it?
Yeah. If we're gonna go that precise, we should take a look for it.
Let's say the force of precision. This is for gravity, right?
Yeah.
6.67.
Hopefully this has it here.
Nothing has it.
Why don't they give me the units I want? Oh, here it is. I don't know.
For core they have
Yeah.
9.80665.
9.80665 for core.
Yeah. 9.8.
It would be nice to get one additional confirmation of that.
We need to send a letter to Harvard, Berkeley, or
The publisher of the book, people do send
for
letters.
confirmation.
All right. Well, we'll just, since we have two, and hopefully this person from Quora is, you really can't trust
No.
Quora. And I'm surprised that
Should we memorize?
Hmm?
How many significant figures should we memorize?
Most people memorize it 2, 9.8.
What did the other one say? It said Wikipedia says 665.
665, 9.80665. All right, we'll go with that. 9.80665. We'll hope that Wikipedia is correct. You don't have to memorize this number, so don't bother memorizing it at all. This is a constant. Okay, the density of the liquid we're going to assume is a constant. You know, we aren't going to go like miles. If we want miles, then the density is different. You know, it's like under the ocean. You know, if you go like 30 feet underwater, does the density of water change that much? No. But if you went, let's say, 15,000 feet underwater, do you think the density is going to be higher? Yeah. Yeah. And so the density of water is, at least for the distances we're using, is constant. Here, this is what makes this nonlinear. What makes this nonlinear is the density is not constant over 6,214 miles. And therefore, this equation fails, because this is a linear equation here. In fact, we'd have to use calculus. We use calculus when things change, like density. If the density is continually changing, the higher we go up, then we need calculus. And this is why calculus is such a powerful tool. We can do those types of calculations. And so this equation would fail here, but this equation should work here because, you know, over 30 feet, I don't think the density is going to change that much for water, right? And so what we're going to say is the density of water, what is the density of water? Density of water is going to be close enough to what? 1.0, you know, for water. For mercury, it's a little different. You know, this is for water. And then we're going to just say that this is pretty much a constant too. And so if G is a constant and D is a constant, then the pressure of the liquid, in this case the pressure of water here, is equal to a constant times D. Well, if the pressure is equal to a constant times D, then let's just use D. Not D, sorry. H. H is not a constant. Is equal to a constant times H, then let's just use H to indicate the pressure, because that's the only thing that's changing. And so this is why we can use the height rather than the actual pressure to indicate it. If we wanted the actual pressure, then we'd have to multiply H by
The constant.
G and D. Once we and we have to change the units here because we need this in kilograms. Here, the density in kilograms, in order to make the units work out. Newtons are kilograms meter square, a meter squared per second square. But anyway, going back to this, and so the pressure of H2O liquid is directly proportional to the height. And so we use the height or the length to express these. So what kind of calculation are we going to do? Are we going to actually calculate the pressure in newtons per meter squared? No. Or pascals? No. We're not going to do that. What we're going to do is we're going to do a simple comparison, you know, of liquids. And so what we're going to do is we're going to compare water and mercury here. And this is why we're going to use this. And so what is the pressure of the water over here?
30 feet.
Okay, the pressure of the water, H2O, you know, 30 feet, yes, because we're using the height. But the actual pressure of the water over here is equal to G times D of water times H of water. Okay, what is the pressure of the mercury liquid over here? The pressure of the mercury liquid here is equal to G times the density of mercury times the height of the mercury. And so what I want to do is I want to do a more precise calculation. You know, where did I come up with 30 feet? And so let me show you where I came up with 30 feet. where I came up with 30 feet is these two weigh the same. Therefore, these two have the same pressure. And so what we're going to do is we're going to just make them equal. So the pressure of the liquid water is equal to the pressure of the liquid mercury. The pressure of the liquid water is equal to G times D of the H2O times H of H2O. And the pressure of the mercury is equal to G times D of mercury times H of mercury. Okay, G is the same. The gravitational constant doesn't change. And so what I'm going to do is I'm going to calculate the height of the H2O. I want to calculate a more precise height because I'm just ballparking 30 feet. I want to know precisely what is that height to as many sig figs as I can. And so I know the height of the mercury already because 1 atmosphere is 760 millimeters of mercury. So this is what I'm going to do. I'm going to solve for the height of H2O. The height of the H2O is equal to the density of mercury over the density of water times the height of the mercury. So what I need to find out is what is the density of mercury. And so let's take a look here at the density of mercury. They give us the density of mercury here to what? 6 sig figs?
Yeah.
You don't have to memorize that, that's for sure. But the density of mercury is 13.5951. 13.5951 grams per cubic centimeter. And the density of water, we're just going to use 1.0 grams per cubic centimeter. So the cubic centimeters cancel. So mercury is 13.5 times more dense than water. And so what that means is we'll need 13.5 times more water than mercury. Okay, and so that's going to be times the height, 760 millimeters of mercury. And so let's calculate this out here. So I have 13.5951 times 760. 10,332. 10,332. I'm only allowed like 2 sig figs here because of the density of water. If I pick the temperature, then I can get the density of the 6 sig figs, and then I can get this answer to 6 sig figs if I wanted. Millimeters of mercury, which is 10.3 meters. Oops, not of mercury. This is going to be of water now. This is the height of the water, so mercury is going to cancel. And so this will be height of H2O, sorry. And so this will be 10.3 meters of H2O. And so I'm guessing a meter is about 3 feet, and so this is 30 feet. This is the type of application that we do. So if you're, let's say, on a mountain here versus at sea level here. Let's say this is sea level. If you're down here at sea level, you're going to have 14.7 pounds of atmosphere weighing on you. But let's say you're up here at the top of this mountain, you're going to have a lot less pressure. Now it's non-linear, the pressure. And so if we use some calculus, we can figure it out. But we don't need calculus because somebody else figured out the equation using calculus. So if somebody else figured out the equation using calculus, then what we can do is we can go ahead and use that equation that somebody else derived for our calculation. And so let's do that. Let's pick some kind of tall mountain. Here. In fact, I like this book because they talk a lot, this is a Canadian book, but they talk a lot about California. 117, we have noted that atmospheric pressure depends on altitude. Atmospheric pressure as a function of, this is number 117. As a function of altitude can be calculated with an equation known as the barometric formula. So somebody figured out the barometric formula because the density changes as we go up. And so this is the pressure of air, or atmospheric pressure. The atmospheric pressure is equal to P0 times 10 to the minus mgh over 2.303 RT. And this is an empirical equation. We're just going to use it. In this equation, P and P0 can be in any pressure units. For example, torr. P0 is the pressure at sea level. So what should we do? Should we do it in atmospheres, or should we do it in torr, or should we do it in millimeters of mercury? What's your preference?
We should do it in atmospheres.
Atmospheres?
Atmosphere
Okay.
might be the best way.
Yeah, let's do it in atmospheres. So this is going to be 1 atmosphere. P0 is just your standard pressure. Okay, times 10 to the minus m. Okay, what is m? So, okay. P0 is the pressure at sea level, generally taken as 1.00 atmospheres, or its equivalent. I just said exactly 1 atmosphere, because that's what it's defined. And so I just have infinite sig figs in mind. The units in the exponential term must be SI units, however. SI units, so we got to think about SI units. Use the barometric formula to estimate the barometric pressure at the top of Mount Whitney in California, altitude 14,494 feet. So we're going to go to the top of Whitney, which I have it backwards. The little ones are on the left, the big ones on the right. But that's okay. The drawing's not very good anyway. 14,494 feet of elevation, altitude. Assume a temperature of 10 degrees C. Well, it's a lot colder there now, but in the summer that seems about right. 10 degrees C is the temperature. All right. So M, what do you think M is?
Looks like molarity from here.
It looks like molarity, but
Yeah.
it's
It's
not
not.
molarity. M,
Maybe it's something similar.
yeah.
Max.
I don't know if you guys know about, in physics you learn about gravitational potential energy. Let's say if you're down here versus if you're up here. If they're both not moving, stationary, then there's no kinetic energy. But there is a difference in energy, right, because there's gravity. And so this is gravitational potential energy. The gravitational potential energy is going to depend on the mass. The heavier, if this were a feather versus a person, they're going to have different masses. So if a feather fell down from here and hit you on the top of the head, would you worry?
No.
No, not that much.
That wouldn't worry so much. But if this person fell down on top of your head, then that would hurt probably.
It would be
Absolutely
very
hurt.
and
Yeah.
also concerning as well.
Yeah, it would be. I see. I see the like at the certain rock climbing places. Little kids running around here below, people climbing up here. I just worry. If somebody slips and falls and lands on the little kid, it's going to be bad. Yeah, because they weigh a lot, and so the mass And it's also going to depend on G. Like if this were on the moon, maybe he'd survive, you know, on the moon, because the force of gravity on the moon is, you know what the force of gravity on the moon is compared to Earth? You could have an instant diet if you go to the moon, because you'd weigh like 1/6 of your mass, because of the gravitational pull on the moon is like 1/6 that of the Earth. That's for weight. Your kilogram mass will be exactly the same though, so it doesn't quite work. G, and then what else? What do you think H is?
Height.
Height. And so the higher you are, the more energy you have. This is gravitational potential energy. Potential energy. So the height. So MGH. Well, that's what I think this is, MGH. Yeah, the M is capital. Do you know what it's indicating?
Movement.
The mass. The mass. How much does this weigh?
Judging from the capital letters of M, I'd say it might be massive.
I know how much it weighs down here, 14.7 pounds. Right there. But you know what we're going to do here for M is, you know, that looks kind of like, you know, because normally it's little m like this. And sometimes we see a big M to indicate the molar mass. Sometimes. The molar mass. But that's a good question. How do we handle the M there?
Yeah, it's capital there, but you can
Right, and it doesn't really give us enough information, does it? And so one of the things that people do in these, sometimes you have to look for different sources. You know, so the book might not be enough because there's kind of a hole in the book. So this is one of the things I'd like to do when I was a student, is I'd like to look it up in different books and see, you know, maybe a different book would explain it a little bit better, you know, what that M is, because our book doesn't say anything, not a peep. And so we might guess it's a molar mass, but what we could do is, well, this is the barometric formula, and so we can take a look at the barometric formula online and see what they do for M.
Quick question. So for the barometric formula, is the R the same as in the combined gas law? 6.2023.
The R?
The R, 2.30
Oh, yeah.
RT.
Right.
Is it still constant?
Well, you know, there are two R's that people either memorize or derive.
There's two?
Yeah, there are two R's. I think you probably learned them earlier. The two R's are different units. 6.022 times 10 to the 23rd. What are the units here?
Atoms or molecules?
6.022, that's not R.
Yeah.
What is R? That's
That's
Avogadro's number.
Doesn't it have a number?
0.2023?
What is R? 0.08206 units?
Kilogram? No. Is it degrees Celsius? Kelvin?
Close. Liters times atmospheres divided by moles times
Kelvin.
Kelvin. Okay, that's R. You have this one memorized?
No.
I thought I did.
I got a little bit.
Yeah, you probably had it memorized at one time, right?
I thought it was 0.80000000.
I thought it was 6.2023.
Gas law constant.
That's the
So
gas.
this is the gas constant. Do you know there's another set of units for this? Joules per mole Kelvin. Do you know what the R value there is in joules per mole Kelvin? Close, yeah. It's 8.31. 8.3145 joules per mole Kelvin. Actually, you only need to memorize one of these. Well, it depends if you have another conversion factor memorized. Oops, I didn't want to erase that. Shoot. Mount Whitney. Mount Whitney, you know Mount Whitney has the main peak here, and then, do you know what this one is?
No.
Keeler Needle, and this is Day Needle here. If you ever go up there.
The highest I've gone is Big Bear.
What's that?
The highest I've ever gone is Big Bear.
Big Bear? Okay.
Yeah, unless you consider it an airplane.
Well, we could calculate the pressure of Big Bear instead. Do you want to?
No.
Oh, it's fine, we already had the height.
The highest I've gone
I
is
already put
probably
my height down.
Because probably Yosemite, and that's how high as I can go.
Okay.
Molar mass.
Yeah, it was the molar mass. Oh, it would be helpful if they told us that, right?
Yeah.
I mean, but they didn't tell us that, so we. Do you know what the molar mass of air is?
Right there.
Right there, but we calculated. Is that the same number we calculated? Do you remember the number we calculated?
No.
The number we calculated was 28 point,
Well, yeah.
but this is 0.028.
Yeah, this is kilograms per minute.
Yeah,
Not by
this
a
is
long
what,
shot.
this is SI units. It's gotta be in kilograms, not grams. So we calculated, what was it? Does somebody have it in their notes?
It's probably somewhere.
Okay, 28.964 is what we calculated.
Oh, so we were missing a 4.
Oh,
Yeah, it would be 28.964 grams per mole.
Right.
This is kilograms per mole because it's SI unit.
right, right, but I just kind of wonder what we calculated.
Let's see how far back I can.
Well, it's a useful number.
I can almost guarantee I wrote it down.
I took a picture of it.
I write down all the numbers.
Oh, I got it, 28.97.
28.97? All right. Close. So maybe their composition was off, or maybe ours was rounding error. You know, we're off a little bit. You know, but that happens quite a lot, and so we gotta. This is why it's nice to have something like the CRC. You know, CRC, the data is pretty up to date, and air, the composition of air varies. You know, a little bit. Oh, here's G. 9.80665, so there's our additional confirmation of G. This is a universal gas constant. I did it as, except which one do we use? Do we use this one or this one? And it turns out we used, looks like we used this one here. Joules per mole Kelvin. All right, so let's try it now. So this is going to be 1 atmosphere times 10 to the minus, okay, in kilograms, which one do you want to use? The one we calculated or this one over here?
Let's do the one that's on the.
All right, this one's more precise, so 0.028, 9644, 9644 units, kilograms per mole. We could have figured out M, because how are we going to cancel out moles? Oh, actually, no, it doesn't really matter. Here, actually, are we going to be able to cancel out moles? I don't know.
From R.
Yeah, R can cancel.
Yeah, R's got to cancel, that's right.
But in order to cancel out R, the temperature would need to be in Kelvin.
Yes. And then G, well, let's go ahead and put in this G over here, 9.80665 meters per second squared. That's our G. And H is, we got to convert it to meters. So what was the elevation again? It was
14,494 feet.
14,494 feet.
Was it?
Anybody else been to the summit of Whitney?
No.
No?
I've been to Yosemite.
I've been to the summit of Whitney and I just had a massive headache. Altitude sickness.
I mentioned Yosemite, but not the mountains.
It was probably due to a combination of dehydration and the hike, to climb up. Because, you know, in Colorado, you can drive to 14,000 feet. And when I drove to 14, I think, was it Colorado? Yeah. You can drive to 14,000 feet. Didn't have a headache then. But then I wasn't exerting myself at all either. So we're gonna convert feet to meters. And so this is it. I don't want you to Google any conversion factors. We should be able to do this based on the conversion factors that we know. If I see like weird conversion factors, I often wonder, you know, where did you get that conversion factor? Did you have that conversion factor memorized? You know? And so some people had it, will have a conversion factor in, let's say, how many centimeters in a yard, you know? Where did they get that? Did they have that memorized? Is that appeared on, or did they search it up? You know? Maybe they had it memorized, maybe they just like to memorize, you know, obscure conversion factors, but it makes me suspect. Yeah, that's why verbal tests are often, are done. Like when you go for your PhD, they give you, they give you a number of verbal. As an undergrad, you don't have that many, or if any. Depends on how big the class is. If the class is very small, they will sometimes give you a verbal
Like
test.
words?
No.
The smallest class I had 4 students.
What class?
That was cosmochemistry.
Class like that.
Cosmochem.
That's.
I was just looking for a class, I just picked that. There are 4 students, and so
Cancel it?
it was at UCLA. I was the only undergraduate, and there's 3 graduate students and me. You can take graduate classes there. Sometimes they're easier than the undergraduate classes. But it's like every quarter at UCLA I go, whoa, that was the hardest, Yeah. And then the next quarter is even harder. So then I stopped, I gave up. And just figured that each quarter it's gonna get harder and harder. So anyway, going back to this,
We convert from feet to centimeters.
okay, what is the conversion from
Sorry.
feet to centimeter? Now that's sometimes I
Feet
see
to
that.
inches.
Sometimes I see people convert straight from feet to centimeters and they'll have the conversion factor and I wonder where the heck did that come from? Do you have it?
I don't know. I would
No.
do.
Does
feet to
anybody have the
inches and then
conversion
inches
from
to
feet to centimeters?
I would do feet to inches and then
Or-
inches to
Centimeters, yeah.
Or,
Just
well,
That's
centimeters are not the SI unit. What's the SI
We
unit?
have to go to meters.
We have to go to
So
meters.
feet to inches, inches to centimeters,
Well,
centimeters to
well, some
meters.
people will write the feet to meters conversion right here, and I think, where the heck did that come from?
it pulled out.
You got it?
Feet to meters?
Well, feet to meters, no, from memory I'm talking
No,
about.
not from memory,
What is it?
no. 3.28.
Alright.
All right, and so then I'll see that, 3.28 meters per foot. Or it's gotta be the other way, 3.28 feet per meters.
Yeah.
Yeah, per meter. Okay, but we shouldn't do that. We should just rely on the ones we know. So we're gonna go feet to what?
Inches.
Inches, so 12 inches per foot. And then inches to centimeters, so 2.54 centimeters per inch. And then
Centimeters to meters.
centimeters to meters. So 1 meter is 100 centimeters. And so when I see this, then it makes sense to me. And that way you can minimize the amount of memorization you have to do. Because if you memorize how many meters or how many feet are in 1 meter, then that's a lot of additional memorization to do, for exams or whatnot. And then there's so many different, possible. So let's figure out how many meters this is. In Europe, they express the mountain heights in meters. Actually, in the rest of the world, they do.
Aren't we?
But they don't make sense to me.
Yeah, pretty much.
What's that?
Pretty much.
Aren't we the only country besides like one other place?
Yeah.
We
It's like us.
do not want to change.
Well, of course, that's why it changed from the imperial system to the American system, because it's ours now.
The only ones left.
Even England doesn't do it.
I think it might be due to our rebellious ways.
I think we're a little bit more organized at this point.
Get this shoe, like grimy shoe.
Okay, well, wait, 4,470.
Yeah, 4,400 meters.
Yeah.
Oh boy.
So the height here is gonna be 4,417.7 meters.
I'm surprised this didn't break my very deep calculus.
Divided by 2.303 R. Which R did we decide? we're
We
gonna
chose joules over mole times K.
use? Yeah, the reason I chose the second one is you should know the definition, well, you eventually should know the definition of a joule.
Meters per second squared,
Meters per second squared.
Kilograms,
kilograms.
meter squared per second squared. And so that's what we're gonna use here. And so when we plug in R, we're gonna go 8.314. Actually, I guess we could use that. Should we go that many digits?
Now let's
Just do it.
Sure, I guess. 8.31444598. Okay, rather than saying joules, I'm gonna write kilograms, meter squared, per second squared, per mole Kelvin. And then the temperature,
it was 10 degrees Celsius, but to Kelvin that's 283.15.
283.15 Kelvin, thank you. So we're gonna invert and multiply this.
Thank you.
When we do that, the Kelvins cancel.
Yeah. Yeah, Kelvin.
Yeah, let's
cancels.
just make sure the units work out. Kelvins cancel, good.
Kilograms cancels with our first one.
Yeah, Kelvins cancel, kilograms cancel,
Along with moles.
meters squared
Yeah.
cancels,
And so does moles.
second squared cancels, moles cancel. All the units cancel. Well, that's what we need. We can't have any units in the, and so let's go ahead and calculate this.
Alright, I got it.
Oh, do you? Okay,
Yes.
tell me.
I did the entire thing.
Wow.
To 6 decimal places, this is 0.586
0.586
8905.
8905 atmospheres. So 0.6 atmospheres. So if we're at the top of Whitney here, we're at 0.6, let's just say 0.6 atmospheres. If we're at the top of Everest, then we're about 0.3 atmospheres. You know, top of Everest, it's non-linear. If we're down here at sea level, then we're at how many atmospheres?
1.
14.
Yeah, we're at 1 atmosphere at sea level. Let's say I go for a swim. I go for a swim and I'm at 10 feet. If I'm at 10 feet underwater, you know, that's about the most I want to go underwater. It's too much pressure. How many atmospheres am I at?
The difference would be too small and still be 1 atmosphere.
Really?
Because you're only 10 feet underwater.
10 feet underwater kills me.
Is a lot.
Is it?
Is the water.
It's too much pressure. You know, is it really about the same, do you think?
I would say it's about the same because once you go below, like,
Okay, how
100
deep do I have to go? Let's go 30 feet. If I go 30 feet underwater, what is the pressure?
more than 1.
It's twice as much underwater as it
One
is
atmosphere.
above water.
Yeah. So what we have here is we have 1 atmosphere of air and 1 atmosphere of water. And so the total pressure here is 2 atmospheres. So if I go 30 feet, I'm under 2 atmospheres of pressure. And so if I'm at 30 feet, that's 2 atmospheres. If I'm at 10 feet, that's 1/3 of an atmosphere. So if this is about 1.3 atmospheres. 1.3 atmospheres is about my limit. Before, I'd have to get something for my ears or
You just have to
something.
clear your ears.
Yeah.
I would say, I don't know.
What's that?
I said I wouldn't.
Okay.
It's free diving.
But you know, there's people who go crazy. They go, what, 60 feet underwater or something like? What was there? There's some kind of world record that just happened?
I've gone 30, 40.
Wow. What is that difficult or is that not? So I mean, I guess if you're,
You have to have the lungs to do it.
so you did that free?
Free diving. Yeah.
Wow. Oh, that's impressive.
If you can hold enough air,
Uh-huh.
you just have
Let's
to
say
clear
I
your
can't
ears.
go that far.
You gotta clear your
It has
ears?
to be a lung,
Okay.
the pressure of the lung.
Yeah, that's what I don't do. I don't clear my ears.
I said, I get motion.
The 60 feet would be what, 3 atmospheres?
That's why flying planes is horrible.
Assuming that the density is
The pressure don't perfect that lot.
All right, so this is talking about liquid pressure.
But I'm thinking of myself.
Wow, that was all.
He's like, I'm the champion now.
That was a fun calculation, but my calculator is smoking. It hates exponents.
Part B here, show that the barometric pressure decreases by 1/30th in value for every 900 feet increase in altitude. It's kind of non-linear, so, you know, over a short range, yes, but over a longer range, no, it's going to change a bit. And so part B, skip part B. This is a homework problem, but it's a homework problem that's kind of missing some stuff. So.
So we're gonna skip part B
Yeah, skip part B
on the homework?
on the homework. Yeah.
Alright.
This was number
117.
117.
Should I read? It's like way too far.
I cannot promise you're gonna follow.
As I can just redo it.
That kind of.
The B's were
So how do we measure atmospheric pressure?
atmosphere to millimeters.
Or what instrument do we use?
A
The
barometer.
atmosphere? I was gonna say the atmosphere, joking,
This is kind of weird.
It's called.
Which of these 4 do you think has the highest pressure?
The biggest one.
Yeah, but
The tallest.
this one,
The
right?
widest.
This one seems to have the highest pressure.
Because it has the highest volume.
It has the highest volume, so it weighs the most, right?
Yeah.
But pressure is an intensive or an extensive property?
Intensive.
It's an intensive because we divide it per square inch, right? And so it's pounds per square inch. And so if you're thinking about pounds per square inch, then, you know, well, yes, this is bigger, so it's gonna weigh more, but then it's also got more square inches. You see that, then something like this and something like that. And so it turns out these 4 have all the same pressure because the pressure of a liquid depends only on the height. Because it is an intensive, it's normalized. And so that's kind of weird because, yeah, I would have thought this one weighs more and this one weighs more, you know.
Yeah, I was thinking
This one would weigh the least, but,
pressure is equal to volume.
yeah. And so, how do we measure pressure? We measure pressure using this instrument. What's this instrument called? Barometer. And this is just a balance. On one side you have the weight of the air. On the other side you have the weight of the mercury. If the air weighs more, then it's going to push the mercury up higher. And so here we have, let's say, what does this show?
The first one's uncapped, the second one's capped.
Okay. Yeah, so on the first one, we have the weight of the air outside and we have the weight of the air inside. Now, yeah, but it's normalized per square inch. And then so it's gonna weigh the same per square inch. And so the pressure inside and the pressure outside are different. In the second one, what they do is they have a vacuum here. And to create a vacuum in here, what they do is they fill up this tube all the way and, well actually first, they have an empty tube. So they flip this upside down and they fill it all the way up with mercury, cap it, and then put it upside down in this liquid. So this tube used to only be filled with mercury. There was no air in there. And so this is a vacuum here. And so there's no weight of gas here. The only weight is the weight of the liquid mercury here. So if we have 14.7 pounds of air here, then we need 14.7 pounds per square inch of mercury out here. 14.7 pounds per square inch of mercury is 760 millimeters tall. Now, if the pressure decreases, these are weird.
Yeah, one's taller and then one's shorter.
I don't know. Let me see if there's a
I
better
don't
one.
know what, I understand A and B, but not the rest.
Yeah.
I think it's if you
Then
have
there's probably an explanation
There's an
somewhere.
explanation, but it's not worth it. Yeah.
The explanation's not worth the time.
I was like, the
It's
C
not
and
worth
D
the time.
were different sizes.
We got
but-
12 minutes.
Yeah, we don't have much time left, so.
I like 10 minutes.
12, we're counting down seconds.
I know,
We
but
need to be specific, 3 significant figures at least.
So barometer, we have a barometer in the lab that you can use to measure.
I need these emails.
So the pressure of the atmosphere is equal to the pressure of the liquid inside the barometer. So if the pressure of the atmosphere goes down, then we don't need as much liquid. If the pressure of the atmosphere goes up, then we need more. And so what we do is we have a line here, and this line is like this. The weight of the atmosphere outside is going to equal the weight of the liquid inside here. And so the two weights are equal. And so this would be 14.7 pounds here and 14.7 pounds here per square inch. And so it's like a balance. That's a barometer. Do you know what this is?
That's,
This is a manometer. We have two types of manometers. We have the open-ended manometer and the closed-ended manometer. Manometer is not for measuring the atmosphere, the weight of the atmosphere. The manometer is for measuring the weight of a gas sample. And so over here we have gas sample weighing on this. This is actually mercury here. And over here we have the atmosphere weighing down here, the barometric pressure. And here, in this case, the two levels are equal, so that means the weights are the same. Over here, the gas weighs a lot more, so what's going to happen is like a seesaw. So this weighs a lot more, the atmosphere weighs less, and so we're going to get this imbalance here. And it turns out we set the horizontal level to the lower level here. So the weight of the gas here is equal to the weight of the atmosphere, the barometric pressure, plus the weight of this liquid. The weight of the liquid here is just equal to the height. And so if the barometric pressure is 760 and this height were 20, then the total weight of this gas would be 780. Over here, the atmosphere weighs more than the gas. And so the atmosphere is going to equal the weight of this liquid, mercury here, from this level, and the weight of the gas. So the weight of the gas is equal to the weight of the atmosphere minus the weight of the liquid mercury. Now, Petrucci doesn't like negative signs. And so Petrucci has some formulas for this, which I don't really like. For me, okay, let's look at this. The weight of the gas is equal to the weight of the atmosphere, the barometric pressure. Over here, the weight of the gas is equal to the weight of the atmosphere plus the weight of this mercury. So the weight of the gas is equal to the weight of the atmosphere plus the weight of the mercury. Over here, the weight of the atmosphere is equal to the weight of the gas plus the weight of the mercury. Therefore, the weight of the gas is equal to the weight of the atmosphere minus this. But Petrucci doesn't like the minus there. So the weight of the gas is equal to the weight of the atmosphere minus this liquid, because it weighs less. So instead, he doesn't like a negative sign here, so what he says is to make sure that delta is negative rather than positive. You see that?
Yeah.
So he throws in a negative here. I don't like that myself.
Delta P.
Does that make sense?
Yeah.
And I don't like memorizing which delta P is negative, which delta P is positive. I don't like that. And so it doesn't make physical, visual sense, but that's something that Petrucci does, not just for this problem, but for multiple problems.
Delta P needs to be defined in every single.
Right, and so my equations are going to be different. You know, for the last scenario there, I'm going to have the weight of the atmosphere, barometric pressure, is equal to the weight of the gas plus the weight of the mercury. And therefore, the pressure of the gas is equal to the pressure of the atmosphere minus the pressure of the mercury. This is the equation I write. rather than plus the pressure of the mercury, which is what he calls delta P. Delta P is just the height. Okay. So that's pretty much it for gas pressure. So we talked about all these units here, I think.
Are they going to be normalizing a specific pressure unit to use universally, like a constant, instead of the interchangeable 5, like just a definitive one?
No.
Okay.
Yeah, getting people to agree on stuff is very difficult.
No, I can only
Look
imagine.
at all
Yeah,
America,
I mean, look at us.
We're still using feet.
You know, when you listen to the weather on the news, it's like inches of mercury, right, rather than millimeters of
Do they
mercury.
really?
Yes,
Yeah.
I listened to the news this morning.
That's terrifying.
Oh, yeah.
What's wrong with us?
There's a lot wrong with us, but we're special.
Well, yes.
And so at least chemists are like halfway between because we're using millimeters of mercury, but people don't want to use millimeters of mercury. People want to use millibar now, and we're all supposed to switch over to bar. But there's some resistance to that.
I'm sorry to think that we are kind of a special people.
Yes.
America is a special place.
Yeah, it's a special place. We're full of special people, so that's why.
Very interesting special people.
My mama says I'm a special boy.
So, all these people are special. Boyle, Charles, who else is there?
Avogadro?
Avogadro, Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law.
You could say Blaine
Now,
Pascal.
Pascal's pretty.
But you know what? We're gonna.
I don't remember all these laws.
The only law that people really remember is Charles' law. Do you know why?
Because it's easy to remember.
Because it's easy.
I mean.
The reason why people remember Charles' law is because it sets a theoretical limit to the lowest temperature we can have. And that is, can you go to a negative volume for gas?
No.
No, the smallest volume of gas you can have is 0. So if we extrapolate Charles' law all the way to 0 volume, what temperature do we get?
Absolute zero.
Absolute 0, minus 273.15 degrees Celsius. Or 0 Kelvin, if you like Celsius or Kelvin, whichever scale you want. And so that's why people remember Charles' law, because Charles' law sets the absolute bottom for temperature. But there's also Gay-Lussac, Boyle, etc. Well, you know what? I'm not gonna test you on the names.
I'm still gonna write down the names because I've been touched on it before.
Yeah, unfortunately, I'm not gonna test you, but on some standardized tests, they do test you on those kind of things. But instead, what I like to do is combine all the simple gas laws into the combined gas law. Do you remember what the combined gas law looks like?
I know what the combined gas level looks
I
like.
remember the name of it.
Yeah. T1, B1
Ah, yes, yes.
over, this is the Chem 1A version.
NRT.
N1 T1 is equal to T2 B2 N2 T2. So this combines Charles' law, Gay-Lussac's, Boyle's law.
Oh, never mind, we never did that one.
I know that.
I remember that one very
Wait,
much.
what is it called?
The combined gas law, or our book calls it the general gas law.
Oh,
Actually, it doesn't even call it law, it just calls it the general gas equation.
alright.
Nice guy, name it after.
Oh, who's missing out? You could have something named after him.
But laws typically are just these empirical equations for this.
Now, were these scientists egotistical because they named these equations after themselves?
No, I just think they were uncreative because they named it after themselves.
Not all of them, some of them are named in honor.
I think I forgot them.
Yeah, I think so. But others named it after themselves, yeah. There is an ego involved there. There's a lot of ego in science too.
Like
You
a
know,
little bit.
And so some people will have, Actually, it's, there are a lot of personalities as well. So anyway, standard, do you know STP?
Yeah.
Standard
Yes.
temperature and pressure, what is it?
Was it 273.15 Kelvin, 1 bar?
Okay. It used to be, this, it used to be 0 degrees Celsius and 1 atmosphere. That was standard temperature and pressure.
Yeah.
Now it's 0 degrees Celsius and 1 bar, STP. But the problem is, who works at STP?
No.
No one.
Absolutely.
So I learned STP and I memorized it, and I never used it. I only used it for homework problems, and I used it in some gas catalogs. They'll give you the STP volume, so they'll say the STP volume is this, and then you can compare. But otherwise, you know, or was it STP volume? I can't even remember. STP density. Otherwise, it's been, and even then, it wasn't very useful. But that's it. This, I added Avogadro's law to this. This is why I threw the ends here. And so this is with Avogadro's. We're going to use Avogadro's law separately, though. And so we're going to do a couple of Avogadro's law type problems here next time. Because we can do Avogadro's stoichiometry. Avogadro's stoichiometry is nice and easy. And other things, as Avogadro's mixtures and etc.
Which law is P1 over T1 is equal to P2 over T2? What's their name? Who made it?
Boyle.
Boyle?
Was it Boyle as pressure and
Boyle was
volume?
P1 V1, P2 V2.
Yeah.
There's too many of them.
And then there's Boyle could have been temperature, I forgot.
Boyle was pressure and volume.
Pressure and volume, then
Yeah,
that's.
Charles was volume and temperature. But
And-
there's one
and-
other. for
yeah,
pressure.
Maybe we
pressure
should
and
just
volume.
Named them for what they are, not after the beginning.
Yeah.
I kinda have to think.
Unfortunately, some standardized tests will